Hello there everyone, my name is Sho, and today we're talking about Googology, that is, the study of big numbers. How big, you might ask? Well, let's put down our billions and trillions for a minute, because we're looking at numbers far bigger than, say, the observable universe. Far bigger than we could ever write down with normal numbers. In fact, so big that in normal life, we just don't need to care about them. That's right, this video is going to have next to no practical applications, so if recreational maths isn't your thing, thanks for swinging by for the first minute or so. You're more than welcome to tune out if this doesn't sound appealing. No judgment. Still here? Alright, let's start off with a very simple question to begin with. How do we get up there from our land of ordinary relatable numbers? I mean, sure, we can keep sticking zeros on the end of a number, but eventually your arm's going to get tired, or your keyboard's going to break, or your computer's just going to crash. No, we're going to need some tools a little stronger than that to get where we're going. Some of these tools might be familiar with normal math, some of them we'll put together as we go. To start with, let's cast our minds back to when multiplication was first taught to us. Now, I'm sure many schools teach multiplication like this. Multiplying a number is adding that many lots of the first number together. For instance, 3 times 5 is just 5 threes added together. And in general, A times B is B lots of A added together. So well and good, and a lot of us learn to avoid all the adding together later on, especially when decimals come up. But I feel it's worth revisiting because we're going to be building on this concept in a minute. We can get bigger numbers by repeating something simple over and over. Now again, later on we're taught powers in much the same way, multiplying that many lots of the first number together. So again, here we have 3 to the 5. It's the same as 5 threes multiplied together, and that's 243. And in general, A to the B means B lots of A multiplied together. Again, doesn't work quite that neatly when decimals come around, but we're not worrying about those for the moment. Just want to observe that. I mean, with exponents, we can get bigger numbers a lot faster than we could with multiplication. Or I guess we're still using multiplication. But either way, I'd just like to show a couple examples of some, well, I suppose most people would call them big numbers. For instance, just a 10 and a 12, we get 1 trillion. That's the largest number most people would name if you asked them to name the biggest number. Also the number we'd use to talk about the total wealth of the world. That's about $400 trillion last I checked. Or we can use a 10 and an 82. Two small numbers on their own, together, estimate the number of atoms in the universe. How much stuff is there? That much. It's going to be one of the last numbers we talk about that has any physical meaning, so enjoy it while you can. Stepping up to 10 to the 100, we have the Google, for which this whole field is named. It was named by a 9-year-old boy in 1920, and we'll be coming back to him shortly, along with another of his contributions to the field. And then to finish off our list, we have the largest prime number we know, at least as of the time I'm recording this video. It's got nearly 25 million digits, so to save time I haven't written it out. You're welcome. Still, something seems a little disappointing with that last number. I mean, yeah, it's a massive prime, that's fairly major. But it's much larger than anything else we've talked about, for sure. But like, we had to use a number in the millions to make it. Can we do better? Introducing the second of the numbers invented by 9-year-old Milton Sirota, the Googolplex. Originally defined as 1 followed by writing zeros until you get tired, his uncle formally standardized it as 1 followed by a Google zeros. His uncle, by the way, was a mathematician in his own right, Edward Kasner. Now, this number dwarfs any attempt to describe it physically. Even if we took every atom in the universe and scratched a million zeros all over its surface, we still wouldn't get there. We still wouldn't be close. In fact, we'd be about a trillionth of the way towards writing it down. So with that in mind, it's clear that doing more than 1 power is much stronger than just making the numbers bigger. But it's important to do it the right way round. After all, doing it in reverse gives us a much smaller number. That's only like 1,000 zeros. You can fit that in an average novel chapter, with room to spare. So yes, when we're doing this sort of calculation, we want the big number on the right. So I made a big fuss about exponents being repeated multiplication and all that. You can probably see where we're going with this. Is there an operation that's repeated exponents? Certainly is, and it's called tetration. Now, as you might imagine, tetration produces even bigger numbers from small inputs than exponentiation does. For instance, 3 tetrated to the 3, here represented with 2 up arrows, represents 3 to the 3 to the 3. We work down from the top. So 3 to the 3 is 27, and 3 to the 27 is about 7.5 trillion. If instead we'd been tetrated to the 4, well, we'd have an extra 3 at the bottom here. So that'd be 3 to the 7 a bit trillion. It's not quite on par with Googolplex, but it's closer than anything else we've said so far. It would also take a very long time to write down. General A tetrated to the B means, well, it means this. A tower of A's B tall, and you work your way down from the top. A Googolplex is somewhere between 10 tetrated to the 3 and 10 tetrated to the 4. And pretty much every number we're going to run into in our modern lives is less than 10 tetrated to the 2. Now, can we go further? And do we have to keep making up names for these operations? I mean, we've got to run out at some point, right? Eventually, we probably would run out of names. Thankfully, someone much smarter than me already had this idea in 1976. Donald Knuth described his up arrow notation as follows. You start with 1 arrow, which is exactly the same as exponentiation. We all know how that works at this point. Then, if you have n arrows, A arrows B is the same as A followed by 1 less arrow, and then the original expression, but you took 1 off of B. You keep doing this repeatedly until B is 1, and you end up with B repetitions of the next operation down, which is exactly how we built up tetration, out of B repetitions of exponentiation. The wonderful thing is, this works for whatever number of arrows you like. All eventually ends up as a truly enormous tower of exponents in the end. And once you work your way down from the top of that tower, you end up with a mind-boggling number. Well, most of the time. If A and B are both 2, then it doesn't matter how many arrows you throw in the middle, you just end up with 4. It just collapses all the way down to 2 to the power 2 is 4. And with this, we have our first major tool for making actually big numbers. Don't worry, Next video is going to show how we can use these arrows to make one of the most famous big numbers of all. And we're going to introduce a ranking scale used in Googology to measure the strength of our tools. Till then, just consider this function, or this expression. How big is it, really? Because we're coming back to it next video. Goodbye.